Welcome to the AP Physics video lecture on Unit 10, Mechanical Waves and Sound. The section is on properties of waves. What I would like you to take a look here is to see the connection between the wave and the simple harmonic motion. The simple harmonic motion of the mass that is oscillating, that is attached to a spring, is similar to the circular motion. If we trace out the circular motion path, it will represent a standing wave right there. So here, this is the connection. A simple harmonic motion will trace out this standing wave. Let's take a look at the characteristics of a standing wave here. The highest point on the waves is called the crest, also referred as to your maximum in math. The lowest point is called a trough, which is going to be your minimum value on the graph. The amplitude is going to be the distance from the equilibrium to the height, or from the equilibrium to the trough. Okay, it is relative to the equilibrium level. So the amplitude is how high the crest can go or how low the trough can go. It is the distance away from equilibrium. The distance between two consecutive crests or two consecutive troughs is going to be considered a wavelength. That is going to be written in that Greek level called lambda, and that represents a complete cycle. So on top there, when you see it from this crest to this crest, that is the graph of a cosine wave. Frequency, also written in that subscript F, has the unit hertz, and that represents the number of cycles per 1 unit of time. Normally, a unit of time is 1 second. So we normally take a look at how many cycles of that wave in 1 second. That is what hertz is referring to. The period, capital T, which is the unit in seconds, that is the time for one complete cycle. Normally a cycle is 2 pi because that's what our circle is. And the connection between frequency and periods are their inverse of each other. So F is equal to 1 over T. Likewise, T is equal to 1 over F. Let's take a look at a problem where we can determine the characteristics of this wave. The scenario here is a transversal periodical wave travels along a rope. The graph shows the vertical position of a particle on the rope as a function of time. First question, what is the amplitude of that wave? So we go from the equilibrium to the crest, and that has the value of 0.20 centimeters. Next, what is the period of the wave? And we know that the period T of the wave is the time to complete one cycle. That is one complete cycle when it starts down here, goes up, down, and it goes back to that starting position. That time would be 4 seconds. So here we would say that the period is 4 seconds because that's how long it takes to complete one cycle. Likewise, what is the frequency of the wave? The frequency is F is equal to 1 over T, so we can substitute that value in for the period that we got in the last question. 1 over 4 is equal to 0.25 hertz. That is going to be the frequency. The frequency here is represented in the next question where it asks, what does that value of 0.25 hertz mean in this context of the wave? That means that there is 0.5 waves at 1 second, because that is what frequency is defined as, the number of wavelength per 1 second. So what is in green here represents the 0.25 of that wave that occurred in 1 second. So that is how frequency and period are related, and that is how you determine it from a graph. Let's take a look at the speed of the wave. So let's remember what our velocity equation or our speed equation is when it is in a line. So this basketball here is traveling on this horizontal surface. The velocity here is equal to the delta x over the delta t, which is the change of position over the change of time. We could just separate it. So delta x can be separated times 1 over delta t, which is representing the delta t that was on the bottom end of that fraction. We do this so you could see the two parts. The delta x here represents the change in the position, and the delta t here is the time that occurred for the ball to roll. Likewise, in a wave, we can see it as a wave traveling on a standing rope. The velocity here is the same as lambda over t. We can split that, so lambda gets to put out, and we could have a 1 over t, which is 1 over the period. This should be familiar because it should look like the equation on top. But we know that 1 over t is in other shorthand for the frequency. So you can see that as just lambda times frequency. This should make sense because lambda is the wavelength. It is red because it is similar to the position. And the blue is the time that occurred and which is on the bottom. So please note that the equation for the velocity of an object traveling on a linear surface is very similar to the velocity of a wave. The red, which is the change in the position for an object, is like the same as the wavelength. The time that occurs, which is blue, for an object to move that distance in a line is like the period, which is also in blue, for a wave to have one cycle. So here I color coded for you so you can see the similarities between the two. Let's look at a problem where we are asked to determine the speed of this wave. The scenario, two waves are traveling parallel to each other. Wave A that has a wavelength of 5 meters and a frequency of 4 hertz. Or wave B that has a wavelength of 5 meters but a period of 0.5 seconds. So the question, which one would travel faster? The answer, let's take a look. Wave A, the equation that we're going to use is lambda times frequency because we have hertz. So 5 was lambda, which is the wavelength. The frequency is 4, so we can multiply it by 4, getting you 20 meters per second. This is the speed of wave A. Wave B, we actually have the period. So we write lambda times 1 over t because we have the period. Plugging in the values, the period was 0.25, so we plugged it in. We do the multiplication 5 times 1 over 0.25. This gets you 20 meters per second. So notice both waves here are the same speed. You might think that they're different, but they're not. The 4 hertz is the same thing as having a period of 0.25 because of that relationship. So there you go. That is everything that you need to know when it comes to the characteristics of a standing wave as well as the speed of a wave for the AP Physics 1 exam.